Hello, my name is Ian Minnick, and today I'll be teaching you about the ideal Brayton cycle. The Brayton cycle was originally developed by George Brayton back in the late 1800s. It is a thermodynamic work cycle that usually involves a working fluid in either air or water. In this instance, we're going to be assuming it's water, and then four components: a pump, a boiler, a turbine, and a condenser. So we'll start here at state 1, which is just liquid water. Now, to get from state 1 to state 2, we have to pass that water through a pump and also add work into the system. This raises the pressure of the water and the temperature of the water. To get from state 2 to state 3, we have to send the water through a boiler. This boiler boils the water and increases the temperature and turns it into steam. From state 3 to state 4, that same steam is then sent through this turbine, which then turns that heat and pressure of the steam and turns it into usable work. From state 4 to state 1, the steam that is then condensed into liquid water after going through the turbine is sent through the condenser, and the rest of the heat of that system is expelled into the atmosphere. Now, because this is an ideal cycle, we can make some very critical assumptions. The first assumption is that all processes on here, going from state 1 to state 2, state 2 to state 3, state 3 to state 4, and so on and so forth, are all reversible, meaning to go back from state 3 to state 2 requires no extra thermodynamic work or energy. Our second assumption is that across the heat exchangers, our boiler and our condenser, the pressure remains absolutely the same. There's no pressure changes from state 2 to state 3, and from state 4 to state 1. And our third and final assumption is that across our pump and our turbine, our entropy value stays exactly the same. So, in order to calculate how much work this system actually does, we first need to calculate how much heat enters and exits, and how much work the system produces and absorbs throughout the entire time. Now, doing this, we need all of our enthalpy values, our H values. If we do not have all of our H values, then we cannot do any of these calculations. So the general equation is to find the work of our device, or the heat entered into our device, is our enthalpy of our second state minus the enthalpy of our first state. So for example, take this boiler. We take the enthalpy of our state 3 and subtract it from the enthalpy of our state 2. That'll give us how much heat enters the system. Now, if your value comes out negative, that means either the heat or the work is leaving the system. So, moving on from that, I will now show you what the T and S diagrams, our temperature and entropy diagram, relates to. The temperature is measured in degrees Celsius, and our entropy is measured in kilojoules per kilogram Kelvin. So we start here at state 1, going to state 2. Notice from our third assumption, the S stays exactly the same. It is absolutely vertical. This is where work into the system originally starts. Going from state 2 to state 3, this is across our boiler, where the temperature increases, and so does our entropy values. From state 3 to state 4, this is where work is leaving the system through our turbine. And obviously from state 4 to state 1, this is where the rest of the heat is leaving the entire system. Now, moving on to efficiency. We can calculate the efficiency of the cycle using this equation down here. Our efficiency is equal to work of the turbine, subtracting the work of the pump, all over Qin, the amount of heat entered in through the system from the boiler. But, like I said, if we do not have all of our H values, calculating the efficiency that way is not possible. However, we can calculate it if we know our maximum and minimum pressure using this equation over here. 1 minus 1 over the pressure max over pressure min to the K minus 1. The K minus 1 divided by K. That equation right there is generally how we can solve it without it. And the efficiencies of a Brayton cycle usually run around 35 to 50%. Now, the final thing here that is important with Brayton cycles is the back work ratio, which is the work of the pump over the work of the turbine. Because the work of the turbine that is actually produced also produces the amount of work that is needed for the pump. And this is usually around 50%. It's not a very efficient cycle. So, to wrap it all up, I told you what the Brayton cycle is, what all the different components of it they are, what it means for this to be an ideal cycle. I explained how to find the entropy, enthalpy, the work and heat entered and exited of the system of this entire thing. I explained our T and S diagram, and I explained our efficiency and back work ratio. Thank you very much, and I hope you learned a lot.